All right, so welcome everyone to this last seminar of the virtual version of the Stochastics and Statistics seminar. It's my great pleasure today to welcome Alexandre from CNRS and École Normale Supérieure. So Alex is actually also a former colleague of mine. He works on optimization. He comes from an optimization background and did his PhD with Steve Boyd. And he's actually had a fairly significant impact on the use of optimization in machine learning, and in particular, the use of semi-definite programs. So if you've used some semi-definite programs to solve machine learning problems, this was initiated largely by Alex. Famous work includes Sparse PCA, Gaussian and Ising graphical models, and more recently, Alex has moved on to more a bigger variety of problems. I know I like to actually follow what Alex does because he always finds some really nice topic and something I can actually run through. For example, has inspired my work on the seriation and learning permutation. And I actually still remember when I described the Shapley-Folkman theorem. So I'm very happy to find it again in this talk. So Alex will, one particular feature of Alex's work is things actually work in his papers. So I hope we'll see something that actually works pretty well here. So take it away, Alex.
Okay, thanks very much, Philippe, for the invitation. It's always a pleasure to visit MIT, and I'm looking forward to the lunch. So yeah, I'm going to talk about feature selection and the Shapley-Folkman theorem, and hopefully the second line is going to be clearer in a few slides. But I should start by saying that this is joint work with Armin Askari and Laurent Ghaoui at Berkeley and Quentin Redjoc at EPFL now. So feature selection probably doesn't really need an introduction, but just in case, the idea is to try to reduce the number of variables in a classification problem, for example, while preserving classification performance. And one of the objectives, of course, is to improve test performance, especially in a high-dimensional setting where samples are scarce, because typically useless variables that you can prune out then act as noise. And if you can remove them, this acts as a sort of regularization, and you typically improve test performance. But in general, the main objective of feature selection is more to help interpretation. If you isolate a small number of variables behind a certain classification or regression problem, you have a better chance of understanding the mechanism behind what you're observing. And so this is the key objective here. For these methods. And of course, this is a highly classical problem. There's a long list of, again, super classical methods to solve it. One of the most famous examples is perhaps LASSO. L1 logistic regression is very, very heavily used as well. Recursive feature elimination for support vector machines, etc. So it's really a workhorse of modern machine learning, and it's a classical pre-processing step in many pipelines. And the reason why it's so heavily used is that it's actually where most of the time in a very nice scenario where, in practice at least, a typically small number of variables explains a very large percentage of the total information in your problem. So that's a very naive example we ran on a real data set on a gene expression data set on lung cancer versus controls in a data set that has 35,000 genes and 2,700 examples. And so again, we have a disclassification task, and we try to select a small number of features explaining a maximum amount of likelihood in this case. And what you can see is that the curve grows very, very steeply in the first part of the graph. So the first, say, 5,000 variables explain something like 80% of the variance. And that's a fairly common phenomenon. So most of the plots of this type actually look like this. It doesn't really matter what the application is. Usually on natural data, a small list of variables completely dominates the picture. And the point of feature selection is to isolate these variables. So here, for example, the main objective in this experiment is to isolate a small list of genes that discriminates between cancers versus control patients. It's a totally naive setup. We just wanted to use real data, but don't use the list of genes below for anything meaningful. It's just to illustrate exactly how these things are used in practice. So that's a typical plot. And again, why do we care about selecting the variables? Well, this is another example in fMRI. So there's been, now that we have high resolution fMRI machines, there's been a lot of work trying to correlate activity in certain regions of the brain with performing a certain number of actions. And so we put people in fMRI machines, we show them pictures, and then we monitor the activity of their brain after these actions. And we try to localize the processing of this information inside the brain. How do you do that? Well, you run the classification problem on activities, and you do feature selection on the voxels predicting a certain type of activity. And if you're lucky and your feature selection technique works, you're going to show that all the active voxels or the selected features will be localized in a certain region of the brain. And you can try to then understand how the brain processes visual information. So that's an example taken from the parietal team at Inaya. Okay.
So how much better does feature selection work in these kind of applications if you include some geometric localization in your objective value? I presume
to get that, typically you use structured penalties to try to localize the feature selection result. So that it's completely out of the scope of what I'm going to talk about today, but clearly one of the big issues with this particular type of experiment is to try to impose some geometrical constraints on the set of selected features, if I understood your question well. Okay, so like everything, feature selection should not be abused. So this fMRI example is a very good way of illustrating one of the key issues with the feature selection, which is false discoveries. It's one of those classical examples where you have an exponential number of hypotheses to test. So you try to identify the support set of your features. So you have an exponential number of feature sets, but typically a polynomial number of samples. So the potential for false discoveries is very high. And at one point, there was a constant stream of papers doing these fMRI experiments without taking care of the false discovery issue. And some researchers decided to sort of make a statement about that. And so they took a dead salmon and put it inside an fMRI machine. And they run the same thing where they showed images to the dead salmon and tried to discriminate between certain images using the dead salmon brain activity. And sure enough, they found some signal. So that's the plot on the image on the left. So just a quick caveat, watch out for false discoveries in feature selection. The number of hypotheses you're testing is always exponential. Your data set, on the other hand, never is. And so you should be careful. Don't try this at home without adult statistical supervision. Okay, but that's not the point of what I'm going to talk about today. The idea is really that in essence, feature selection is a high-dimensional problem. Otherwise, there would be no point in selecting features. So it's important for these techniques to scale, right? And in practice, among the long list of classical techniques to perform feature selection, we typically have methods that require solving optimization problems. So LASSO, for example, solves a penalized QP. Linear SVM solves a penalized convex minimization problem. And so if you're talking about very, very large scale data sets, the complexity of solving these problems can become quickly prohibitive, right? If your data set is not so large, then it's fine, but then the point of feature selection is probably not as important. And that's the first point. The second point is that we have recovery results on the support for many of these techniques, or for some of these techniques at least, but they require fairly stringent and hard to test incoherence or restricted isometry properties, etc. And which typically mean that your features are uncorrelated in a certain way. So that's one side. So optimization problems with guarantees, but stringent assumptions and relatively high complexity. On the other hand, you have techniques such as ANOVA, TF-IDF, etc., which work variable by variable, which are of course infinitely cheaper and naively parallel, but their performance in practice is much weaker. So that's the sort of very, very quick description of the current trade-off from a computational perspective. And so the idea today is to try to see what we can do in terms of feature selection with technique that is arguably very, very classical, which is just naive Bayes, right? So that's basically filtering spam in your email. And the question is, can we come up with a sparse version of naive Bayes, and the sparsity being there to select features, okay? And so I'm going to spend some time on that, and then we'll try to see how well this thing performs. We're going to focus on a multinomial version of naive Bayes. What I'm talking about applies also to a binary version, and if we take the limit, we might do Gaussian, etc. So multinomial is fairly clean, and that's what I'm going to focus on today, but it's something that can be worked on. So if in a multinomial model, the conditional, the maximum likelihood problem looks like this here. It's fairly straightforward. F plus and F minus is the sum of the vectors of feature vectors corresponding to positive and negative examples, respectively. You then solve this maximum likelihood problem, which has a closed form solution. You get a vector theta star plus and a vector theta star minus. And typically you stop there, but if you look a little bit at the way this model is then used, you can look at the classification using naive Bayes as following a linear classification rule. And so you classify a new point by looking at the sign of V plus W transpose X, where W is this vector computing the difference between the vector theta star plus and the vector theta star minus. And so how do you do feature selection in this case? When you have a linear model, feature selection means zeroing out a certain number of coefficients of W. And here this means some of the values of the coefficients of theta star plus are equal to the corresponding coefficient in theta star minus, right? So again, multinomial naive Bayes, you solve the maximum likelihood problem, you end up with a linear classification rule. If you want to do feature selection, you look for zeros in this vector W, which is the difference of the logs of the theta stars, of the theta plus and theta minus, right? So if we want to produce a sparse version of naive Bayes, we need to modify the maximum likelihood model to include a sparsity constraint that is going to zero out a number of the coefficients of the vector W. And that means basically penalizing, since W is the difference, there is a zero in W if the coefficients of theta plus and theta minus are equal. What you want to do is to penalize the number of non-zero coefficients in the difference theta plus minus theta minus. So that's the penalized sparse version of multinomial naive Bayes. Okay, it's a non-convex optimization problem because of the cardinality constraint over here. K is the target number of features. And so it's something that's easy to write, but the question is now, how can you solve this problem? And in particular, can you write down a convex relaxation? And if you can write down a convex relaxation, how good is it? And can you derive approximation bounds? Okay, and so I'm going to spend the rest of this talk discussing these two questions. And thankfully, the first one has a very easy answer. And so it turns out that the dual of the sparse multinomial naive Bayes problem. This one here has a very simple format. It's actually a one-dimensional convex optimization problem, right? So you get an upper bound on phi k, the value of the optimum value of the sparse multinomial naive Bayes problem, by computing psi k, and psi k is simply some constant c plus the minimum over the scalar variable alpha between 0 and 1 of sk of h alpha, where sk is the sum of the k largest coefficients of the vector h alpha, and h alpha is this vector here. And it's formed using the sum of the positive feature vectors and the negative feature vectors, f plus and f minus. So solving a one-dimensional convex optimization problem is something we fortunately know how to do. And you can do this by bisection. And the good news is that the complexity is linear. So basically solving the convex relaxation has more or less the same complexity as solving the original naive Bayes problem, right? You just pay this k log k term, but where k is the number of the target number of features you're aiming at, and k is typically much smaller than n. So the good news is that we can solve the dual efficiently. The dual will give us an upper bound on psi k. The question is, how far is this upper bound from the true value phi k that we care about? Okay, and so the next question is, can we get approximation bounds for this dual solution? And if the answer was no, I would be talking about something else. The good news is that yes, we can actually get bounds, and they rely on something called the Shapley-Folkman theorem. So I'm going to spend a few minutes introducing this result somewhat graphically. So a small, quick primer on convex duality and the Shapley-Folkman theorem. So just to refresh your memory on these things, the Minkowski sum of two sets, x and y, is the set of vectors x plus y, where x is in x and y is in y. So for two triangles like this, we get this polytope over here. That's their Minkowski sum. And one important feature of the Minkowski sum that we're going to use extensively in what follows is the fact that it commutes with the convex hull operation, so that the convex hull of the Minkowski sum of VIs is equal to the sum of the convex hulls of the VIs. Okay. So why do we care about Minkowski sums? Well, it turns out that Minkowski sums have a convexification effect, right? And we can do a very small experiment that hopefully is a nice illustration of this phenomenon. If we take the L1/2 unit ball, which looks like this here, and we compute its Minkowski average. So we take 2 unit balls, take their Minkowski sum, divide by 2. What we get is this. We do the same thing with 10 L1/2 balls. We take their average, and we get this. And basically, as you increase the number of terms in the sum, what you converge to is this thing here, which is the L1 ball, and is in fact the convex hull of the L1/2 ball. Okay, so that's actually true of Minkowski averages, but it's what's even more striking in a way is that it's also true of sums, Minkowski sums of arbitrary lists of sets. And so in machine learning, when you don't know what to do and where to find data, you use digits. And so we can illustrate this phenomenon with digits. And so if we take the digits 1, 2, 3, 4, and 5 as point sets, so these are non-convex sets of about the same size, and you take their Minkowski sum, what you get is this sort of big blob here, which looks like 0. But the interesting fact, it's been scaled down a little bit to make the picture nicer, but the interesting fact about this set here is that, well, first, it doesn't look that good because it was derived by sort of exhaustive sampling, because there's no closed form solution for the Minkowski sum at that scale. So it's a sort of approximation, but what you can see immediately is that this set is close to being convex, while the original sets are anything but convex. And we're not talking about a very, very large list of sets, where we're talking about 5 sets. So again, here what we see is that the Minkowski sum has this convexification effect, and the Shapley-Folkman theorem quantifies that very precisely. So it's an old result, it dates back from the 60s, but for some reason it's not that well known, and so it's always good to do a little bit of advertising. So what does it say? So suppose you have a list of sets VI in RD, so d-dimensional sets, and you have n of them. And the typical setting here where everything works out fine is when n is larger than d, much larger than d, hopefully. Okay, so this is the picture you should have in mind. And now suppose that we take a vector x in the convex hull of the Minkowski sum of VI, of the VIs, right? This is also the sum of the convex hulls of the VI. And now what the Shapley-Folkman theorem says is that we can actually represent x as the sum of vectors inside the original sets VI, and n of them minus the size of a set S, where x is the sum of n minus s of vectors in the original sets VI plus the size of s vectors in the convex hull of the VIs. And now, why does this describe the convexification effect of the Shapley-Folkman theorem and of taking the Minkowski sum? Well, suppose that n grows very, very large, while d remains fixed. And all the sets VI have about the same scale, right? As n grows and d remains fixed, since the size of s here is constrained by d, this term here is going to quickly become negligible compared to this one. And what this result tells you now is that if you pick an x inside the convex hull of the Minkowski sum, this x can also be represented as a vector inside the Minkowski sum plus a residual here, which becomes negligible as n goes to infinity and d remains fixed. Again, in a setting where all the sets have about the same size, right? What's kind of fun about this result is that it's super easy to prove. And so let's do it. So suppose x is in the convex hull of the Minkowski sum of the sets VI. It's also in the sum of the convex hulls. And if it's in the sum of the convex hulls, we can write it in this sort of augmented format where we stack together the convex combination constraints and the normalization constraints on the coefficients lambda ij, right? So writing that x is inside the sum of convex hulls is equivalent to writing this. And now, for this representation, we have a lot of coefficients lambda ij. We have n times d plus 1 of them. But conic character theory, since we're in dimension n plus d, tells us that we can have a similar representation, exact representation for x1 using at most n plus d non-zero coefficients. And you basically conclude using a pigeonhole argument where, because of the normalization constraints, you have n plus d non-trivial coefficients to distribute. You're going to put n at least in one coefficient at least in each of n spots here, because you need to satisfy the normalization constraints in one. And then you have an additional d coefficients to spread around n sets. And if n is much larger than d, it means you're going to be left with a lot of sets where you only have one convex combination coefficient equal to 1. And in that case, the corresponding vector will be in the original set, not in the convex hull of VI, right? So that's the argument. And what the proof says is that basically the number of non-zero coefficients lambda ij controls the gap between the Minkowski sum of the sets VI and its convex hull, right? And it's just character theory. And so you can make the convergence rate a bit more precise. So what you can say is that, in particular, you take sets VI in dimension d and you bound their radius uniformly by a constant r. then the Hausdorff distance between the Minkowski mean and its convex hull will be bounded by r times the square root of the mean of n and d divided by n. So you have a very clean and immediate estimate of the convergence rate. And so you can show that as d is fixed and n goes to infinity, the Minkowski mean converges towards its convex hull in the Hausdorff metric. And this actually holds in a number of other less trivial non-convexity measures. And there's a very nice paper on that, a recent paper on that by Fradelizzi and others in 2017. Okay, so that's Shapley-Folkman. So why do we care about Shapley-Folkman here? Well, it turns out that, as you might expect, a theorem about asymptotic convexity has very intriguing applications in optimization. And so Shapley-Folkman will allow us to bound the duality gap in our relaxation of sparse naive Bayes. And so we can do that now. Okay, I can take questions if anyone has any, but otherwise I'm happy to move on. Okay, so suppose just generically that we start from a separable optimization problem where we minimize a sum of functions fi of xi subject to a linear inequality constraint. And so again, what's important here is that we have fi of xi. So the problem is indeed separable both in the objective and the constraints. And in this setting, you can it's very easy to form a convex relaxation of that problem if the fi's are not all convex by taking the convex envelope of the functions fi. So you can immediately write down a convex relaxation of the problem P using the convex envelope. And as a quick reminder, the convex envelope of a problem can be formed using the biconjugate. And it's basically a function whose epigraph is the closed convex hull of the epigraph of the original function, up to a long list of technical details. And so that's a very graphical way of forming convex relaxations. You basically look for the largest convex lower bound on the function you care about, and that's a sort of convex approximation of your original objective. What's very interesting for us is that the convex envelope and the function itself match at extreme points of the epigraph. And keep that in mind because it's going to become useful later on. And we can also use the convex envelope to quantify the lack of convexity of a function. And it's just the maximum difference between the original function and its convex envelope, right? So if this is 0, the function is convex, and otherwise this measures, in a sort of worst case sense, the non-convexity of the function f. So again, it's very easy to illustrate these points on a 1D graphical example. This is the function, the indicator of x being equal to 0. Okay, it looks like this, 0 in 0, 1 otherwise. Its convex envelope over the interval -1, 1 is simply the absolute value function here. And what you can see is that, again, at extreme points of the epigraph, here, here, and here, the function and its convex envelope actually match. Okay? So that's classical convex analysis, but it never hurts. So what we can do is we start from our optimization problem, and just to remember how duality works graphically, we can form its epigraph, as in, for example, a recent survey by Le Maréchal and Renaud in 2001. And we can form the dual graphically as the problem of minimizing an affine form over the closed convex hull of the epigraph G, right? So graphically, at least, solving the dual is solving an affine optimization problem over the closed convex hull of the epigraph of your original problem, right? And so what happens, and that's the classical sort of proof structure for strong duality actually, is that if the epigraph itself is equal to its closed convex hull, you typically have no duality gap in P. And the gap in convexity of the epigraph actually characterizes the non-convexity of the problem and the duality gap. And what's important in separable optimization problems like the one we care about today is that the epigraph has a very particular structure. And surprisingly enough, in this case, the epigraph is a Minkowski sum of elementary epigraphs Fi, which follow this definition, right? And so basically, what Shapley-Folkman allows you to show is that all the points in G star star can be represented as points in the original epigraphs of the original functions f. Or in other words, if the number of functions, if n here, the number of terms in your objective function is large enough, and the number of constraints in this case is remaining fixed, then the epigraph of your problem is close to its closed convex hull, and your problem is nearly convex. And it gets more and more convex as n grows and n remains fixed. Here, n is the number of terms in the sum, and m is the number of constraints. And so the main result when you apply Shapley-Folkman to separable convex optimization problems is that these problems become increasingly close to being convex as the number of terms in the sum grows to infinity, while the number of constraints remains fixed, right? And so that's what we're going to use today. These results are also fairly classical. They date back from at least Aubin and Alexandre in the 70s. There's a much more, there's a more modern version that's available in the classical book by Alexandre and Temam in 1999. And so what their application of Shapley-Folkman to convex optimization, optimization problems tells you is that if you start from a separable optimization problem like this one, then you can show that the optimum value of the original non-convex problem is of course bounded below by the optimum value of the convex relaxation, but it's bounded above by the same value of the convex relaxation plus a term that depends on the non-convexity of the functions fi and on the sum of m plus 1 of these non-convexities. And what you see here again is that if n grows towards infinity while m remains fixed, this term here, which bounds the duality gap of your relaxation, will become negligible compared to this sum. And so you can show that as n goes to infinity, your relaxation becomes increasingly tight and the gap goes to 0. There is I'm going to spare you the details, but it's important because this is the result we're going to end up using on sparse naive Bayes. There's a similar result for constraint problems, separable constraint optimization problems with separable constraints, of course, but generic constraints, not simply linear ones. And you can quantify the duality gap in terms of the non-convexity of the constraints and in terms of the solution of a perturbed version of the convex relaxation of your problem, where you have a small perturbation term u on the right-hand side of your constraints, right? Otherwise, the bound looks similar. You still have a bound on the gap depending on the number of constraints and the maximum non-convexity of your objective function terms. And you basically can apply this result almost directly to the sparse naive Bayes problem I detailed just before, okay? You only have one non-convex constraint here, the cardinality constraint. The vector quantifying the duality gap here is constant, equal to 0, 0, and 4. So this models basically the non-convexity of the constraints. And so what this result shows us is that we can, of course, bound the optimum value of the sparse naive Bayes problem, the non-convex one, by psi k, the value of its dual. And that's a problem you can solve explicitly. But the Aubin and Alexandre result tells us that we can also get a lower bound on phi k using psi of k minus 4. So if you can solve the relaxation at value k and k minus 4, you can sandwich the value of the sparse naive Bayes problem. Okay.
So is the Shapley-Folkman theorem constructive, and does it help you with rounding? Because a priori you haven't said anything about actually finding some sort of set yet?
Good question. So the answer is yes, but it's not as simple as it should be. And so I'm not going to be able to discuss that in detail today, because it turns out that in most cases, if you're outside of pathological scenarios, you recover the support of your solution, which is what you actually care about, by looking at the support of the k-largest coefficients in your dual relaxation. And so you basically solve the dual by bisection, complexity is linear, you get the support of the k-largest coefficients after optimizing in alpha, and that support gives you your list of k selected features, right? Unfortunately, that's a trick, and it's not guaranteed to work in every possible scenario, and it actually takes a number of pages to show that you can always, in a guaranteed way, recover the optimum support from the solution of the relaxation, but the argument is much longer, and it's definitely not a direct application of Shapley-Folkman, but I'll refer you to the paper to see how this works, and we can talk about it offline. Okay. But anyway, in most scenarios, you just solve the dual, get a list of k-largest coefficients, and these are your variables, and this thing works. And so that's it. That's the entire story. We have a sparse version of the naive-Bayes problem. We can form a convex relaxation. It's very cheap to solve because the complexity is linear, and we get explicit bounds on the duality gap that do not require any further assumptions and are basically defined in terms of the convex relaxation itself. And so we tried this on a number of examples, mostly using text data at this point, because that's something Laurent is closely interested in. And so we tried various data sets from Amazon, IMDb, Twitter, etc., of sizes ranging from a few thousand to a few million variables. And to give you an idea of the computing times, using a completely unoptimized setting, running feature selection on an example with 12 million variables takes about 13 seconds on a laptop with plain Python code and just using a CPU. So the rule of thumb, if you do an unoptimized implementation, is 1 second per million variables. And the key here is to try to understand how well we perform relative to all these other feature selection techniques. And of course, to properly evaluate the quality of a feature selection method, you need a sort of ground truth. And in most examples, you don't have that. And so the next best thing we thought was to run the feature selection algorithm on a classification problem and look at how much feature selection degrades classification performance or accuracy, right? And so a good feature selection method should degrade accuracy less than a bad one. And so this is one way of comparing feature selection techniques on natural data sets, right? So we tried a number of things. So on the upper right corner, so x-axis is training time in log scale. Y-axis is accuracy, linear scale. And in the upper right corner, you have all these classical techniques like LASSO, logistic L1, etc. We just had a bug with SVM L1 on this sample, and I didn't fix it, but soon enough. But basically, you have one cluster of results coming from these classical L1 penalized techniques, for example, or recursive feature elimination for various sparsity targets, and they're all clustered somewhere here. At the other extreme, you have all these sort of univariate techniques like odds ratio, thresholding, etc. And these are all clustered somewhere here. And our method, so sparse naive Bayes, is somewhere here, meaning that on these text examples, at least, we reach the performance of LASSO, logistic L1, etc. but our training time is about 100 times faster. Okay, and so at least on these text examples, there seems to be very little a decrease in statistical performance, but a speed up of order 100.
Yeah, Alex, I have a quick question.
Yes.
So this picture is illustrating both the performance of the feature selection procedure and naive Bayes, right? Like you're actually comparing how naive Bayes is doing on this data set compared to, say, logistic. Is that correct?
Yes and no, because that's an important thing I forgot. Thank you for the question. It's an important thing I forgot to mention. We run various codes on stage 1 to do feature selection. So in one case, it's naive Bayes. In another, it's logistic regression with L1 penalty. Stage 1, the only thing we keep from stage 1 is the list of selected variables. Okay. Now on stage 2, to compare things on equal terms, we keep this list of variables, but we basically just run a naive Bayes or some other technique on all these selected variables, right? So in fact, we are sort of pruning out the effect of the algorithm itself. All we take as information as input in the second stage is the list of selected variables. So the answer is kind of no. In fact, hopefully, there's nothing else differing from these examples than the list of selected features. Okay? So that's it. Unfortunately, we are doing some other experiments on bio data sets, etc. And it may be because of normalization issues, but the performance is not as spectacular. It works, but it's not as striking. So another important test, duality gap. So these are very naive examples in dimension 30 or 3000. And so what you see here is the solid black curve is the upper bound coming from the convex relaxation. The dotted curve is the upper bound taken at k-4, which should be a lower bound now. And the red dashed line is the result of the optimization, the non-convex solution we get from primalization, which is picking the list of k leading variables. So that's an example in dimension 30. That's an example in dimension 3000. And you can see that in dimension 3000, the relaxation is essentially tight. And what's interesting with the bound is that basically the duality gap depends on the slope of your likelihood curve. And that's interesting because it means that whenever your likelihood is flattening as you're adding variables, the duality gap goes to 0. And when is this curve flattening? It's flattening when you're adding useless variables. So what we can say is that our relaxation becomes tight as soon as you start adding useless variables, right? And that's because of this gap being bounded by psi k minus 4, right? So that sort of makes sense. And so just to illustrate also the complexity in practice, so this is a runtime on a set of IMDb data sets using TF-IDF vectors data, increasing M and K with a fixed ratio K over M. And what you can see in this graph is that the empirical complexity, at least, is sublinear or close to being linear, right? Which confirms what the theory tells you. And because this thing is really useful, it's feature selection, it's supposed to be something you run on very high dimensional data sets. We tried it on one of the benchmark data sets for large scale classification, which is a conversion log from Criteo. And the data set itself is 45 gigabytes. It has 45 million rows and 15,000 columns. And so pre-processing in this case, again, on a single laptop with everything serial, etc. So basically pruning out nans, encoding categorical features, etc. Pre-processing of this kind takes 50 minutes. Computing F plus and F minus, which are the key inputs of your model, takes about 20 minutes. And computing the full trade-off curve here, likelihood versus number of features, the one that typically allows you to determine how many features you want to select. So, which is basically amounts to solving 15,000 sparse relaxations of the sparse multinomial naive Bayes problem, that takes 2 minutes. And so that's again on a standard workstation with plain Python and CPU. The good news is that the first 2 phases, which are the most expensive ones by far, are naively parallel, and this is something you can heavily distribute. But once you have your data set prepared, feature selection itself it is almost instantaneous, okay, which is the point. And so I'm done. If you only remember one thing from this talk, is that for naive Bayes, in the multinomial case at least, you get sparsity for free. Why? Because, well, the complexity remains linear. You have a nearly tight relaxation. And the good news is that, at least on the text examples we tried, the feature selection performance is very comparable to that of LASSO, but the code is 100 times faster. And we don't need any bizarre assumptions on the data set to get these this tightness result. So no RIP or anything like that. On the other hand, we make a fairly serious assumption to begin with, which is the one behind naive Bayes. But beyond that, that's all you need. You get tightness and linear convergence. Okay? And if you want to try it, there's a package on GitHub called Naive Feature Selection, and enjoy. I'm happy to answer questions.
All right, thank you, Alex. So we are going to have plenty of time for questions. Just to remind you a little bit, if you can, if you're visible, please feel free to turn on your camera when you ask a question. It's just a little more pleasant for Alex, unless it's really unpleasant. Yeah, so let's take a few questions. We can have even a small discussion, I guess, at this point. Yeah, please just take the stage.
I have a question about Shapley-Folkman theorem. It might not be relevant to the application that you have in mind, that you discussed here, but I'm just curious. Is there a quantification about the difference in volumes between the convex hull and that sum? Because it might, Hausdorff different distance might be small, but the volume could be large. And if it's small, it might be interesting for the randomized applications.
Yeah, the reference you want on that is this paper by Fradelizzi and others I cited, 2017. And if I remember well, they have something related to volume.
And the answer is
the answer is yes. So this convergence result holds in many different ways.
Okay.
Okay. And then you can again quantify the rate fairly precisely, etc. So yeah, yes, for sure. But that's not me. It's these guys.
Quick question here. So I guess, as you kind of alluded to in your ongoing work, so if that basically you did not report in this talk, if you take a typical non-convex optimization problem, even with separable structure, if you look at a convex relaxation of this based on quadratic relaxations and basically bring it to a STP format and so on, and then if you compare that solution with a solution that relies on separability, you typically get much better results, tighter relaxations from a quadratic relaxation compared to a relaxation which relies on separability, which is the case with the Shapley-Folkman theorem. And I wonder if you had any comments about, so basically what is happening here that allows basically this Shapley-Folkman theorem and the separability to give such nice results?
Honestly, I don't have a good intuition on why, on the relative performance of SDP-based relaxations versus these Shapley-Folkman-based or separable problems. I think the reason why things work out really nicely here is because there is only one non-convex constraint, and so you're in the almost ideal setting for this Shapley-Folkman result, because the size of the duality gap depends basically on the ratio between the number of terms in your sum, which is very large here because it's proportional to the dimension of your feature selection problem, and the number of constraints that are non-convex. And here you only have one.
You only have one, yeah.
So it's the best case scenario for these results. So that's the first thing. The second is that, and that's something I could not discuss today because it's getting too technical, but the primalization it could be tricky. So as Uncle rightly asked. So it's not because you can bound the gap that you can get a good primal solution. And in this case, we are very lucky because it turns out that the second dual, which is left as an exercise, has a very nice interpretation in terms of explicitly forming the convex hull, a solution in the convex hull of the Minkowski sum. And which means that if you solve the dual and its dual, which you can do, you recover precisely the weight lambda I. And if you have the lambda I in the solution, you can compute a good primal solution. And that's not at all a given, but it works out completely fine here. And just a happy accident. So that's probably a long story short.
Thank you.
Other questions for Alex? I guess I do have a question. So when you quoted this Eklund and Temem duality gap result, right? So I was wondering, like, so I mean, it looks like it's very powerful, right? It essentially says, so you stated it as a sum, but essentially if I state it as an average, I'm going to have basically 0 duality gap in the objective function, even if I'm actually minimizing non-convex functions. So
Yes.
Presumably, I mean, this probably indicates that there is still ways to go from, you know, closing the duality gap to actually solving any non-convex problem that you want, which is the average of non-convex functions, right?
Yes.
So, okay. And so the question is, what is the extra ingredient that will make one problem easier than another somehow? Like, is there a general understanding? So you mentioned what was happening for this specific problem, but do you have sort of a general understanding of what allows you to, you know, translate this apparently very powerful duality gap result to some, you know, rounding mechanism?
Yes. So rounding is a second question and it's probably tougher. But for the gap itself, the key quantity that drives the size of this gap is coupling, right? The reason this works and the reason why Shapley-Folkman works is because your problem is separable, okay? Now, you can always make your problem separable by adding dummy variables and adding constraints, okay? But then the entire structure and argument relies on how coupling these constraints are. If your problem is loosely coupled, is a sum of non-convex functions, and you have loose coupling, you're going to get a very good gap. If your problem is highly coupled, you get a very bad gap, right? So the more constraints you have and the more your variables get coupled, the larger the gap. And the problem basically that is not solved now by the current Shapley-Folkman results is that we don't have a sort of soft measure of coupling. We count, so we count terms in the objective, we have worst case bounds on non-convexity, and we count constraints. And counting is always bad, right? Ranks, cardinalities, etc. are unstable quantities. You should not express bounds using unstable quantities. There should be something softer, like a numerical rank or a sort of numerical number of constraints. And that's something that's a bit trickier to quantify. There's a combinatorial aspect to it, and we don't have a clean answer, but there are better quantities you can use to quantify this coupling more finely and get hopefully better bounds on the gap. So one way to see how much margin we have is just to look at the proof of Shapley-Folkman. The current bound comes from applying Carra-Theodori. And we know that there's a considerable amount of slack in Carra-Theodori, right? So in practice, sparse versions of Carra-Theodori gives you good approximation bounds with a control on the number of non-zero coefficients, which gives you a better gap. And we know that even those bounds are very conservative. So you know that in fact,
while you're talking about this, I had this question about, is there an approximate version of Shapley-Folkman where you actually just sample the VIs, like Mori style?
Thank you for allowing me to plug my other paper, which is called an approximate Shapley-Folkman theorem. So yes, there is, but but it's tricky because it means applying approximate category in a setting where you go from n plus d variable to n variables with n large. So you have to use sampling without replacement results, etc., to get finer bounds. But yes, the answer is yes, but it's unfortunately not as intuitive and clean as one would like. And so my apologies to the referees if they are sitting somewhere in the room. But yes, yeah, you can do that. But there's considerable amount of slack all over in the end result. One coming from category, but the other being, for example, that you can, instead of counting constraints, you can count support constraints. And typically the number of support constraints is much smaller. But again, quantifying the support in a sort of soft way is trickier.
Okay. Okay, so since I used most of Alex's question time, maybe I'll let someone ask another question. Is there any question? No? Well, since it's noon here at least, I think we should all thank Alex, at least virtually, and I thank you everyone. So this was actually the last seminar of the semester, and hopefully we'll resume in better condition next semester. Thanks, Alex.
Yep, always a pleasure.